Good morning, students. Myself, Vijay Shankar, EC Electronics and Communication Department, Chevrolet Engineering College. Today, we are going to discuss about the properties of Fourier series in the unit 2 as per the J into Kakinada syllabus. A signal system, properties of Fourier series. See the first property. We already know the Fourier series is used to analyze. The Fourier series is used to analyze for periodic signals, and the Fourier series or the classification of three types. One is trigonometric Fourier series, and the second one is a compact trigonometric Fourier series, and the third one is a exponential Fourier series. So the trigonometric Fourier series, the signal x of t is equal to a of 0 plus sum of n is equal to 1 to infinite an cos function plus the sum of k is equal to 1 to infinite kn is equal to 1 to infinite bn sine function. What are the coefficients of cosine function and the sine function and the constant a of 0 or an by substituting the n is equal to 0, or I can use that as a of k, b of k, and the a of 0. When k is equal to 0, the a of k becomes the a of 0. And we have the a of 0, a of k, and the b of k. Using this, the second classification of the Fourier series as compact trigonometric Fourier series, or it is also called as a polar Fourier series. The signal x of t is equal to d of 0. Whatever the a of 0, the d of 0 is also the same. And the second term with d of k and pi of k. So what is the d of k? D of k is a magnitude of the a of k, square root of a of k square plus b of k square. We already know what is a of k and the b of k. And the phase angle, the cos omega naught t plus phi of k is the coefficient of d of k, and phi of k is a minus tan inverse of b of k by the a of k. Okay, and this compact trigonometric Fourier series we are using to analyze the Fourier series. There's a few, so I'm not in detail how we get the d of k and how we get it is a pi of k and the x of t equations. Now the last one is exponential Fourier series. You have to learn exponential Fourier series. In that is a synthesis equation and the analysis equation. Okay, synthesis equation is the signal x of t is equal to, analysis equation is equal to x of k, and there is a relation between of the two functions. The relation between of the two functions, x of t as a Fourier series relation x of k. X of k is analysis equation and x of t is a synthesis equation. Using these two relations, mostly for the Fourier series, we are using this exponential Fourier series only for analyzing. All the properties also I have to prove that by using the analysis and the synthesis equation. The first property in the Fourier series, we already discussed this one. Again, you can go for the first property, the linearity property. So the x of t and the x of k having the Fourier series relations, as x of t is a signal, x of k is a coefficient of the Fourier series. And the second one, you can take y of t, the y of t having the Fourier series relation with y of t and the y of k, then the z of t is equal to a of x of t plus b into y of t. The Fourier series is a z of k is equal to a into x of k plus b into y of k. So I have to prove that by taking off z of t is equal to the combination of the two signals with the coefficients or the constants of a and the b. Applying the Fourier series for the z of t to get it is a z of k, and that is equal to of x of k and y of k with the multiplication factors of the constants a and b. The first I am taking as a x of k is equal to, what is the x of k? Is an analysis equation. X of k is equal to one by t, the integral, the t values, x of t as a signal, here negative exponential minus j k omega naught t dt. The Fourier series coefficient x of k is equal to 1 by t integral t x of t e power minus j k omega naught t dt. Using this relation, I have to prove the linearity property by taking off z of t as an input function, and to get the, after applying the Fourier series for the z of t, z of k. Follow my dear students. Now I will take the whiteboard and I will explain there. Showing that the linearity property, the first property, linearity, what they are saying, take the z of t, I have to prove z of t is equal to a into x of t plus b into y of t. Fourier series of z of t as z of k is equal to a into x of k plus b into y of k. Right. Take the proof. We know the x of k is equal to the analysis equation of the exponential Fourier series 1 by t, the integral t x of t e power minus j k omega naught t dt. According to the analysis equation, the exponential Fourier series. Take this as x of k is z of k is equal to 1 by t integral t. So what is the x of t now? If it is x of k, here the x of t. Now it is a z of k, here the z of t. What is the z of t given? A into x of t. So directly I am writing a into x of t plus b into y of t. The given x of t is z of t is equal to, and e power minus j k omega naught t dt. Alright, students. Is a very important, the properties of Fourier series, Fourier transformation, Laplace transformation, the Z transformations. The coming units we have. And the second unit is the Fourier transformation, and the last two units are the Laplace and the Z transformations. Okay, these are the very important properties. By using these properties only, you have to solve the problems, or you have to analyze the Fourier series, Fourier transformation for the periodic and the non-periodic signals. Understood, my dear students? So listen carefully. Z of k is equal to 1 by t, the given. Now I can write this integral as two parts, as 1 by t, the integral t, a into x of t. For the first function also there is a multiplication factor of e power minus jk omega naught t dt plus the another integral, the integral 1 by t b into x of, not the x of t, it is a y of t, sorry, y of t. Use the small letters only for the signals, x of t, y of t, and for the coefficients z of k, x of k, you can use the capital letters, my students. Y of t e power minus jk omega naught t dt. Alright. So here the a is a constant and the b is also constant. You can write it as a into 1 by t as a multiplication factor, integral t x of t e power minus jk omega naught t dt plus, and b into, here the I am taking the b as a common, b whole multiplied with the 1 by t integral t y of t e power minus jk omega naught t dt. See here in the parenthesis, whatever the a is multiplied, it's in the parenthesis 1 by t, the integral t x of t e power minus jk omega naught t dt is similar to that of x of k equation only. You see, the x of k analysis equation. So you can write it as a x of k plus, see here also the b is multiplied or within the parenthesis, the one of the equation we have, that is 1 by t integral t y of t e power minus jk omega naught t dt. See, instead of x of t here it is a y of t. So when it is a x of t as a signal, the coefficient is x of k. When the signal is y of t here, the coefficient is a y of k. So a into x of k plus b into y of k. So that only we have to show that z of k is equal to a into x of k plus b into y of k. All I want to say, this is the first property in the Fourier series, the linearity property. Coming to the second property here, the significance of this linearity property. This property is used to analyze signals which are represented as linear combination of other signals. The significance of linear property is used to analyze the signals which are represented as linear combination of the other signals. Okay. So here also the same thing, a into 1 by t, the integral 1 by t x of t e power minus jk omega naught t dt plus b into 1 by t, the integral t y of t e power minus jk omega naught t dt. So a is multiplied with x of k and b is multiplied with the y of k. Fine. Coming to the time shift or the translation second property. time shift or translation. I will show that in the whiteboard. The second property, time shift. Time shift property. What is the statement here? The statement of a time shift property. If x of t, Fourier series x of k, if x of t is the Fourier series x of k, then prove that x of t minus t naught. So the given signal x of t is shifted with the t naught samples. The Fourier series of that is e power minus jk omega naught t naught into x of k. Following my dear students. So in this, you take it as a z of t is equal to, and this one is a z of k is equal. You have to prove that z of k is equal. Okay. The proof of the time shift property. Coming to the proof, we know the signal x of k is equal to, or z of t is equal to. Let us take z of k is equal to 1 by t the integral t, 1 by t the integral t, z of t, e power minus jk omega naught t dt. This is z of t given x of t minus t naught. Okay. Otherwise, some little bit we are having. So this is z of t function, and this is the z of t. Okay, my dear students. Is equal to 1 by t, the integral t. So what is the z of t given here? X of t minus t naught. So I am taking this as x of t minus t naught e power minus jk omega naught t dt. Following my dear students. So how you can prove this by directly? It is not as x of t e power minus jk omega naught t dt. Instead of t here, t minus t naught is there. So keep these two terms as a single term, assuming let t minus t naught is equal to m. Let us assume t minus t naught is equal to m. Here the t naught is a constant. So apply the derivative on both sides. Apply derivative on both sides. So what is the derivative of t dt minus what is the derivative of t naught 0 is equal to what is the derivative of m dm, because t and the m both are variables. Here in this the t is a variable. Now I am changing the t to the m variable. Okay, and the limitations is the same. There is no any change of the limitations, because in the minus infinite to infinite, whatever the t is there, here the m is also the same. So I'm taking the same thing, 1 by t, the integral t, the limitations. So x of, I'm taking the t minus t naught is a m, e power minus jk omega naught. What is the t here? The t minus t naught is equal to m. T minus t naught is equal to m. From this, the t is equal to m plus t naught. M plus t naught. So replace here the t by m plus t naught into dt. Following my dear students. So now in the power there is a two terms are there. Split the two integrations. 1 by t, the integral t, x of m, and e power minus jk omega naught m. Sorry, it is not the dt. It is dm, because we are changing it to the m values. So taking that the dt as a dm. Dm, and another here e power minus jk omega naught into t naught, my dear students. Okay, you see this one, 1 by t, the integral t, x of m, e power minus jk omega naught m dm. This is the same equation here. Instead of t, here the three variables, the variable is a m, and the x of m here, so you can write it as a x of k into e power minus jk omega naught t naught. So this is the same thing you have to prove, the x of k e power minus jk omega naught into t naught, my dear students. It's a very important. So the shifting, how many samples it is shifted, the t naught samples. So for this function, the x of t minus t naught means for x of t, x of k is a Fourier series. For x of t, x of k is a Fourier series. For t naught sampling is shifted, the time is shifting. So see here the timer t. If it is a frequency means k here. Converting of a time to the frequency. Here the frequency is a k. So now here we are taking the time shift only. The time is shifted t naught samples. So it is multiplied with e power minus jk omega naught into t naught. That is a t naught samples. If suppose instead of t naught here there is a another value is there, the 3 or 4 means e power minus jk omega naught 3, 4, whatever it is. Following my dear students. For the shifting of t naught samples, e power the exponential factor is multiplied with the t as t naught, e power minus jk omega naught t naught value. Let's go to the next one. So before going to that, you see here also the z of t is equal to x of t minus t naught. The Fourier series z of k is equal to e power minus jk omega naught t naught into x of k. See the proof, I'm taking the z of k is equal to the Fourier coefficients. 1 by d the integral x of t minus t naught e power minus jk omega naught t dt. Jk omega naught t dt. Let t minus t naught is equal to m. The limits of integration will shift by t naught, but again the integration is over one period. Hence, limits can be kept same. So I'm not changing the limits of t, even if it is a t changes as m. Okay. So see the t minus t naught is replaced with m here, and the t is replaced with m plus m plus t naught. So rewrite the expression 1 by t, the integral t, x of m, the first exponential e power minus j k omega naught m, will multiplied with second exponential e power minus j k omega naught t naught. So within the parentheses, whatever we have here, that is equivalent of the quantity inside the square brackets is x of k. Inside the square brackets is x of k. Hence, z of k is equal to e power minus j k omega naught t naught into x of k. Understand, my dear friends? Okay. The next one. Frequency shift property. Third one. Frequency shift property. The third property it is. Second property we already seen. Second is a time shift property, and the first one is a linearity property. Now it is the third one is a frequency shift property. Frequency shift. So the x of k minus k naught. X of k minus k naught. So let us see the proof of frequency shift property. What they are asking that here, if x of the statement is if x of t, the Fourier series x of k, then z of t is equal to e power j k naught omega naught t x of t. So take the signal as e power j k naught omega naught t x of t. Apply the Fourier series, then the z of k is equal to x of k minus k naught. Z of k is equal to x minus x of k minus k naught. Let us see in the whiteboard here, or otherwise directly I will explain here itself. So z of k is equal to, so what is the analysis equation saying that 1 by t, the integral t, z of t, e power minus j k omega naught t dt. Understood, my dear students? Now I am taking the z of t. They are asking that take that z of t is equal to e power j k naught omega naught t x of t. So z of k is equal to 1 by t, the integral t. What is the z of t here? E power j k naught omega naught t into here the x of t is also there. X of t whole multiplied with, because this is z of t only. Here another function is there, e power minus j k omega naught t dt. J k omega naught t dt. Now, see here the e power is there, and here also the e power. So both the bases are same. Then we can add the powers 1 by t, the integral t, taking the x of t here, x of t. Here the e power, both the e powers only, e power. Here the j is there, here also j. So I am taking the j as a common. Here omega naught is there and the t is also there. So I'm taking the omega naught. Here the minus k and here the plus k naught. So keep the minus here. I'm taking here the k minus k naught. K minus k naught. Now you can see minus e power minus j omega naught k, and e power minus into minus is a plus. For k naught, the exponential is a plus here, and into the t also. So what is the three terms is a common, j omega naught t. I take here the e power minus is there. So minus into plus here the minus, wherever the k is there. And wherever the k naught is present, there is a plus. Minus into minus is a plus, dt. Now you can observe this total equation is similar to x of k is equal to 1 by t, the analysis equation, my dear student. Analysis equation, integral t, x of t, e power minus j k omega naught t dt also. So now you can observe these two equations. So z of k it is here. Observe these two. Here the x of k, this is z of k. 1 by t, the 1 by t, the integral t, x of t here, e power minus j omega naught t, and the k here, dt and dt. What is the value here? The k. So whenever it is a k here, the value is the x of k. Instead of k, what is the value here? K minus k naught. K minus k naught. So total equation, instead of k here, it is x of k. Now the right hand side equation becomes of x of, what is the instead of k here? K minus k naught. K minus k naught. K minus k naught. The frequency, x of k is a frequency, x of t is a time. In the time shift, there is a multiplication factor of e power minus j k omega naught t naught for x of k. But in the frequency shift, frequency is shifted. How many samples it is shifted? K naught samples. So that k naught samples is multiplied here for the time signal. For the time signal, my dear students. Following. So in the frequency shift, exponential factor, that is a positive exponential, my dear students. This is a positive exponential. Positive exponential with the samples of k naught is multiplied to the time signal. In the time shift property, negative exponential with t naught samples are there is multiplied to the frequency x of. Understood? Once again, I will explain clearly. You see what I am saying, the time shift. In the time shift property, that is x of t minus t naught. So there is a shifting in the time with the t naught samples. What is the Fourier series here? Fourier series is e power minus j k omega naught, and since it is a t naught samples is shifted, t naught into x of k, the coefficient. Alright. In the frequency shift, see here, frequency shift means shifting occurs in the frequency. The shifting is in the frequency. So x of k minus k naught, my dear students. So in this case, the time is shifted with the t naught samples. In this case, frequency is shifted with the k naught samples. So now, the x of t is multiplied with, so in this case, x of k is multiplied with a negative exponential. In this case, the x of t, the time signal, is multiplied with the positive exponential e power j. How many samples it is shifted? K is the frequency. So k naught samples, k naught. But here I am not taking the k naught here. T naught. K naught omega naught into t. Now you can understand. So in the time shift property, the frequency or the Fourier series coefficient is multiplied with this factor. And in the frequency shift, the time signal is multiplied with this factor. E power j k naught omega naught t. Here, e power minus j k omega naught t. Okay, my dear students, see here the z of t taken as e power j k naught omega naught t x of t. E power j k naught omega naught t x of. So remember this one. The time is shifted with the t naught samples is multiplied to the, after applying the Fourier series, the Fourier coefficient x of k is multiplied the negative exponential with the t naught samples. But in the frequency shift, with the shifting of frequency k naught samples, the time signal is multiplied with positive exponential e power plus j k naught, because it is a shifting the k naught samples, k naught omega naught t x of. Okay, my dear students, now you can understood. Then coming to the next one, fourth property, scaling property. Till now we discussed about the linearity property, time shift property, and frequency shift property. Now coming to the fourth property, scaling property. Scaling property. Here you have to remember the two words for the scaling. So already we've seen the basic operations on the signals, the time scaling we have. The time is scaling with A. If A is greater than 1, A is less than 1. In the greater than 1, there is a compression is occurs. When A is less than 1, expansion is occurs in the time scale. But in the Fourier series property, the scaling, if x of t, see here, the statement saying that if x of t, the Fourier series x of k, then take the z of t is x of at. What we know this one? We already heard in the basic operation of the signals x of at. Apply the Fourier series for this signal like z of t to get the x of k by using the exponential Fourier series equation only. But have to remember these equations, these statements, not the equation, sorry, these two statements. Since x of t is a periodic, why I am saying is a periodic, the Fourier, remember that the Fourier series is used to analyze the periodic signals only. Once again, I am saying the Fourier series is used to analyze for periodic signals only. See, the x of t is a periodic. If x of t is a periodic, then z of t is equal to x of at is also periodic. Is also periodic, and if t is a period of x of t, see here, it is a very important point. When x of t is a periodic, x of t is periodic. It's a very, very important point, my dear students. If x of t is a periodic, what is a period here? 1 by t, the integral t, we are taking that. T is a period. T, the capital T is a period of x of t. Is a period of x of t signal. Understood, my dear student? Because it is x of t is a period. Now we are taking the x of at. If x of at is also the periodic, is periodic, if x of t is a periodic, is a scaling with a. For x of t, the t is periodic, means for x of at, the t by a. T by a is a period. T by a is the period of x of at. Remember, my dear student, this is a very important. Okay, for x of t is a periodic, means t is the period for x of t. Okay, for x of t is a periodic, means t by a is a period. T by a is a period of x of at. It's a very important. Z of t will be now than the period of z of t. Why you are saying the z of t? Because z of t is a x of at only. Z of t is will be the t by a. Okay, in the time it is. Similarly, the second point now you can see. Similarly, if frequency of x of t is omega naught, okay, in the terms of frequency, if I am saying the frequency of x of t, the frequency of x of t is omega naught, and the frequency is a frequency. And for the frequency of x of at, x of at is a into omega naught. A into omega naught. Now we can modify these two equations in the analysis equation. This is very, very important. When if it is x of t is a periodic, and z of t, x of at, the period is a t by a. If omega naught is a frequency for the x of t signal, for x of at will be the a into omega naught. So in the frequency we are multiplying the a, in the time we are dividing with the a. In the frequency we are multiplying with the a, and in the time we are multiplying with the 1 by a, the period. Remember. Then we can see how we can prove that it is a x of k, my dear students. Following the proof. See, I will show that there is a proof here. There is no the proof here. I take the whiteboard and I will explain the proof. The fourth property, time scaling. Time scaling. Time scaling property. What is the statement saying? If x of t the Fourier series. So listen carefully, my dear students. X of t, the Fourier series, x of k, then you have to prove x of at by taking of z of t is equal. So z of t is equal to x of at. Apply the Fourier series, you get x of k only, x of k. What z of s? Z of k. Z of k is equal to x of k. Z of t is equal to when we take the x of at. Let the proof. So what is the analysis equation saying? X of k is equal to 1 by t integral t x of t e power minus j k omega naught t dt. Okay, my dear students. Now I am replacing the x of t. Means here it is not the x. Little bit confusion will get. I am taking only the z. So z of k is equal to, and it is a z of t. What they are saying, take the z of t is x of at. Now I am substituting the 1 by the t integral t, replacing the z of t as x a of t. Following, my dear students, x a of t e power minus j k omega naught t dt. What we said, when x of t is periodic, t is the period. T is the period. Okay. And if x of at is a periodic, what is the time here? Period. The t by a. T by a is the period. Okay, my dear students. T by a is a period of x of t, and here the period of x of at. So now I am changing this as a t by a here. In the denominator only the t by a. And these limitations is also the t by a one. Okay. Because it is a minus t by a. And what is the frequency? This is the time. The frequency for the x of t, the frequency is omega naught. For x of at, the frequency is a into omega naught. Okay. So when I am replacing this x of at, the frequency is changes as a into omega naught. So time period is changes the t by a, and the frequency is increases. So there is a relation is there, my dear students, when the time is decreases. Why I am saying it is a decreases t by a. What is the frequency? Definitely is increases all, because there is an inversely relation between of the time and the frequency. If time is decreases, the frequency is increases. Okay. For this, we are taking the t by a here, means definitely the frequency is increases, because the t and f, the frequency, is inversely relation between. If this is increases, means this is a decreases. If this is a decreases, means this is a increases. Following my question. So t by a is decreases, means definitely the increases of the frequency. Okay. Now take that. Assume AT is equal to M. AT is equal to M. What we did in the time shifting property, the replacing of x of t minus t naught as a M. Here also I'm taking the same thing. Okay, then t is equal to, what is it? T is equal to M by A. T is equal to M by A. Apply the derivative on both sides. So dt is equal to 1 by A into dm. 1 by A into dm. Don't confuse here. Applying the derivative, we get dt is equal to, because the t is a constant, and the A into dt. And m is also the variable, so dm. So I cross multiply here the A as 1 by A into dm. That is equal to 1 by t by A means the A will get in the numerator and t will get here. And integral the t by A or whatever it is in the minus infinite to infinite only. So again, the value is in the t on the t to t limitations only. X of m, since I assume the AT is equal to m, e power minus j k A into omega naught. What is the t here? M by A. T now it is m by A. Omega naught it is m by A. What is the dt? Dm. Dt as a dm. Okay, my dear students. Now the A get cancelled here. A get cancelled. And see the 1 by the t integral t x of m e power minus j k omega naught m and the dm. Okay, and this equation actually, this equation is when the A is equal to 1 here. And it is becomes of the same equation, see here. Instead of z of t, here is x of m e power minus j k omega naught m and the dm. Simple, it is x of m, not is a small letter, the capital x of k, when this A is 1. A is equal to 1. If suppose it's a A, here it is a 1 only. A is a 1. Otherwise, it's a 1 by the magnitude of A. You get 1 by the magnitude of A, and A get cancelled there. Till finally, we have x of k only. The x of t. Apply the Fourier x of at, my dear students. X of at for the scaling of time, for the time. Applying the Fourier series, you get x of k only. X of k. Understood? Now coming to the another one. So the same thing, x of k is equal to 1 by the integral t x of t e power minus j k omega naught t dt. Substitute the t as a t by a. When we replacing the x of t is x of at, and change this omega frequency also as a into omega naught. Simplify that. Finally, we get the x of k only. Then, fifth property here. It is also important, my dear students. Fifth property, time differentiation. Time differentiation. Okay, in this time differentiation, till now up to the 4 properties we are using in the exponential Fourier series. There is a 2 equations we have. One is analysis equation and another one is a synthesis equation. What is the synthesis equation? See here, these are defined by the definition of x of t is equal to sum of k equal to minus infinite to infinite x of k e power j k omega naught t. This is a synthesis equation, my dear students. We already discussed about this. Okay, I will show that also. The previous slides we have. This is C. Here, x of t is equal to, this is a synthesis equation, x of t is equal to sum of k equal to minus infinite to infinite x of k e power, it is a positive exponential, my dear students, e power j k omega naught t as synthesis equation. Analysis equation mostly we are using for the proofs of Fourier series. The x of k is equal to 1 by t, nothing but is a Fourier series coefficient. X of k is equal to 1 by the integral t e power minus j k omega naught t dt. Omega naught t dt. Understood, my students? So now we go today's class. Is the time differentiation. To prove that it is a time differentiation property, we are using the synthesis equation. Synthesis equation, x of t is equal to. Okay. Now that also, if I am taking here in the whiteboard, take the another one. It's the fifth property, time differentiation. Time differentiation. Okay. What is a statement saying that if x of t Fourier series x of k, then prove that d by the dt, the derivative of x of t, is a Fourier series j k omega naught into x of k, j k omega naught into x of k. And you see that it is a proof by using the synthesis equation. Okay, what is the synthesis equation saying? That x of t is equal to sum of k equal to minus infinite to infinite, minus infinite to infinite. Here, whenever it is output is x of t, the input is x of k, the coefficients. If x of k is the output, x of t is a signal. The positive exponential j k omega naught t. There is no any dt here because it is a summation, not the integral. Okay. Now I am applying the derivative on both sides. Apply derivative on both sides. Apply the derivative on both sides. So d by dt of the d by dt. Now I am applying only for the with respect to the time only. The d by dt is equal to the sum of the k is constant for with respect to the t, and x of k is also the constant, and here the t is there. So d by dt e power not the minus, is a j k omega naught t. Following my students. So here only we have the t. So apply the d by dt in the right hand side, in the left hand side the d by dt is equal to the sum of k equal to minus infinite to infinite x of k. What is the derivative of exponential? E power j k omega naught t, and the coefficient of the t. What is the coefficient of t here? J k omega naught. Okay, this is a factor. You see, this is the same equation. Sum of k equal to minus infinite to infinite x of k e power j k omega naught t. Okay, I'm rewriting this as the sum of k equal to minus infinite to infinite x of k means j k omega naught x of k, take as a single term multiplied with e power j k omega naught t. What is equal to in the right left hand side, the d by dt of x of t. See, what is this equation saying? That x of t is equal to k, sum of k equal to minus infinite to infinite x of k e power j k omega naught t means x of t, a relation between Fourier series relation for x of k. Follow my dear students. See, this is the equation saying that if x of t is a Fourier series, x of k. Same here, instead of x of t, here the d by dt of x of t, sum of k equal to minus infinite to infinite. Instead of x of k, that is j k omega naught x of k into e power j k omega naught t1. So there is a relation between the x of t and the x of k is a Fourier series here. Now, in this equation also, what is the relation? The d by dt of x of t is a Fourier series relation. Since here the x of t, I am taking the x of t, the Fourier series relation. Since here the x of k. Instead of x of k, what is the term here? Total term j k omega naught into x of k. This is a Fourier series relation for derivative factor. The d by dt of x of t, the Fourier series j k omega naught x of k. That only you have to prove. Following my dear students, x of t, the sum of k equal to minus infinite to infinite x of k e power j k omega naught t is an equation of analysis when x of t, the Fourier series, is x of k. If same thing here also, if the d by dt of x of t, the Fourier series of j k omega naught x of k, that satisfies this equation. The d by dt of x of t is equal to sum of k equal to minus infinite to infinite j k omega naught x of k e power j k omega naught t. Understood, my dear students? The time differentiation, the time is differentiated here, t by dt of x of t. If they ask the frequency differentiation means, you can apply the d by dk. With respect to the frequency, we are applying the derivative for the frequency. Understood? So, linearity property, and the second one is time shift property, third one is frequency shift property, and fourth one is a scaling property. For all these four properties, we prove that the statement given for these four statements, using the analysis equation, we prove the statements. But the time differentiation property is proved by using the synthesis equation. This is a synthesis equation. Okay, remember, to prove the time differentiation property, we use the synthesis equation. The remaining 4 properties what we already discussed, we use analysis equation. Following what I should. Now coming to the here what they are saying. So the synthesis equation, or the by definition of exponential Fourier series, apply the derivative on both sides, d by dt of x of t, sum of k equal to minus infinite to infinite x of k. After applying the directly here, j k omega naught e power j k omega naught t, rewrite this expression as d by x of t, dx of t by dt is equal to sum of k equal to minus infinite to infinite j k omega naught x of k e power j k omega naught t. We know that x of t is a Fourier series relation of x of k. By using this equation, we can say that d by dt of x of t means for this signal, apply the derivative to get the Fourier series is j k omega naught, the multiplication factor of x of j k omega naught x of k. J k omega naught x of k minus. Understood? So that only we already proved here. J k omega naught x of k. Understood? The next property, the convolution property, is somewhat different. You have to know what is the equation of the convolution. The convolution between the time and the convolution in the frequency also. Okay, means the time is when we can take it as x of t, the convolution is the y of t is for continuous. For continuous, we are using the integral value. Okay, x of n with the convolution. Convolution means asterisk. We can say in between there is a convolution, not that it is a cross mark, multiplication factor. It is a asterisk, we are calling it as. It's a star in the keyboard. X of n and the y of n, or h of n also. Let us take, there is no any confusion, you can take it as h of t, x of t, h of t, or x of n, h of n, or the y of n also. In this, the discrete functions, discrete time function, the summation we are using is minus infinite to infinite, or it is an integral with the t. And here the summation is also the minus infinite to infinite, or we can take it as n. Okay. This is the equation you have to know before going to the proof of the convolution in the time, the sixth property, convolution in the time. That we see in the next class, my dear students. Okay. In the next class, we can see there's the convolution in time and convolution in frequency, whatever it is. And the frequency differentiation also, if there is. Okay. Is there any doubt, my dear students? Please rise. Okay. Thank you. Thank you, one and all.